Hello everyone, my name is Christian and today I'm gonna give you a brief overview of my research work that will be presented in the International Materials Research Congress. First of all, I want to thank you for your attention. I hope you find this work interesting and useful. The title of this research is Pore-Shape Effect on Mechanical Properties, Thermal Conductivity, and Permeability of Aluminum Foams manufactured by the infiltration method. So I'd like to start giving you some context. So let's begin with some theoretical background, starting with metallic foams. As you may know, these materials are composed of a metallic matrix and a porous phase that is uniformly distributed inside the metal matrix. And they are well known for combining the properties of porous structures or porous materials with the properties of metals and alloys. In this study, we are specifically focusing on aluminum alloys. And well, this is really important because the combination of these two set of properties allow us to obtain very versatile materials. And for example, we can have really lightweight materials with good mechanical resistance or good energy absorption capacity. But in the case of metals, most importantly, we can retain electrical and thermal conductivity. And that's really an interesting approach because when we are talking about porous materials made from polymers or ceramics, we are very limited in talking about electrical and thermal conductivity. Now, the other concept that I'd like to talk about is the infiltration over space-holder particle method. This is a process to manufacture aluminum alloys, and in this process we have to cast a molten alloy over a bed or a volume of removable particles in such a way that the molten metal fills the empty space between these particles. Then we allow solidification, and once the material is fully solidified, we can remove the particles to obtain the final aluminum foam. Although nowadays we have a lot of different processes available, the infiltration method offers a really good set of advantages. For example, we can control in a really precise way the quantity, the shape, and the size of the pores. And this is really important because in this process, the final pore shape is determined by the particle shape. For example, if we use a spherical particle, we're gonna get a spherical pore. If we use an irregular particle, we're gonna get an irregular pore. And this morphology is known for having a really important influence over some of the properties of the foam. So with this in mind, the objective of this study was to use different space holders with different morphologies to manufacture aluminum foams. And once we had the foams, analyze the effect of using these different morphologies on properties like mechanical properties, thermal conductivity, and permeability. This was done by using microtomography for generating 3D reconstructions of experimental foams, and then we perform some computational simulations to measure the effect of the morphology over these mentioned properties. Okay, now we can continue with the experimental and computational method section. As you can see here, the first step was to acquire the base materials. For the space holder particles, we used powdered sodium chloride for the spherical and ellipsoidal morphologies, and the irregular one was directly obtained from commercial sodium chloride. In the case of the alloy, we selected the 319 for two main reasons. The first one is that it has a really high silicon content, This helps to improve fluidity, and this is really desirable for ensuring a full infiltration between the particles. And the second is that it's a really widely available alloy, and it can be recycled many times. Then the second step for this process was the foam manufacturing. In this case, we used an infiltration device that it was developed by our research team and also was patented a few years ago. As you can see, it consists of an infiltration chamber. In this chamber, we place the space holder particles along with the base alloy. And then we put this inside a furnace and we take them to 700 Celsius for 45 minutes. Once the infiltration is completed and the material is fully solidified, we extract the foam and we dissolve the space holder particles with water. Once we obtain all the aluminum foams for the three different pore morphologies, we perform a computed tomography scan for each type of morphology using an X-ray Versa 510 equipment. The scanning was configured to obtain 800 projections, and the next step was the reconstruction of geometries. Here we refine the projections obtained from the CT scans, and we eliminate some residual voxels or parts that were undesirable, such as parts of this plastic support and that we didn't need for the analysis. And finally, we perform the numerical simulations. For the case of mechanical simulations, we use ANSYS Mechanical in its version 19, and we configure the boundary conditions to simulate an isostatic compressive test. This means that we use a displacement in one of the circular faces and a movement restriction in the opposite one using a fixed support border condition. From these simulations, we obtain displacement and force data to calculate the elastic modulus. And in the other hand, permeability and thermal conductivity simulations were conducted in Aviso. In the case of permeability, the configuration setup was a laminar single-phase incompressible flow, maintaining the same flow rate at inlet and outlet, and using a pressure difference of 50,000 pascals with a fluid viscosity of 0.001 pascal seconds, and the convergence criterion was 0.0001. And for the thermal conductivity simulations, the Aviso model used the Fourier's equation under steady-state conditions, and we calculated the apparent thermal conductivity of the foam. We assigned the conductivity values for aluminum alloy and the void spaces. And for aluminum alloy, we use 37 watts per meter Kelvin, and for the void, we use 0.024 watts per meter Kelvin. Now, moving on to the results section, we're going to start with the computed tomography reconstruction. As you can see in figure 1, the accuracy in capturing the structural characteristics was very high in both cases for metal matrix and pore space of the experimental foams. Besides this, we can see in table 2 that porosity values for computed tomography geometries and experimental foams were very similar, with using small variations that are practically negligible, around 2 or 3%. And also we can see that size and quantity of pores are very similar for experimental geometries and computed tomography geometry. Regarding to the mechanical simulations, we can see the results in table 2. And as you can see, we are comparing the elastic modulus, and we can appreciate that there's still a considerable gap between simulated and experimental values. However, it is important to notice that the trend is similar when we talk about geometries, with the spherical geometry having the highest elastic modulus, followed by the ellipsoidal, and finally the irregular one. Now, when we talk about thermal conductivity simulations, we can see that although the measurement direction of the simulation did not produce any significant differences, the spherical cores again showed the highest apparent thermal conductivity. We explain this by the fact that these spherical cores have similar dimensions along their orthogonal axes. This leads to a more uniform and regular pore distribution within the foam, and by consequence, a more regular and uniform heat flow inside the foam. In contrast, we can say that ellipsoidal and irregular pores often tend to have one of their orthogonal axes significantly longer than the other, resulting in uneven pore distribution and therefore a less uniform heat flow. And finally, we can observe the permeability results in figure number 3, and we can appreciate a marked dependence on the shape and orientation of the pores, with the permeability values showing significant variations depending on the measurement direction. Finally, we concluded after this analysis, we get to the following conclusions. We think that we have demonstrated the pore shape effect on aluminum foams using the numerical simulations on the computed tomography and reconstructed geometries. For all the cases, we think that these simulations require refinement. It's important to note that this is just the first approach to these simulations, and we are currently working on improving the models using a better meshing parameters, using border conditions that have better accuracy resembling the actual conditions of experimental tests. Especially in the mechanical simulations that we really have a big margin of error there. And finally, we conclude that these preliminary results will serve as a reference for model calibration and validation. Once again, thank you so much for your attention, and have a nice day.